Hey, let's learn about acceleration today. So, acceleration basically means any change in an object's velocity. So, remember, velocity is your speed in a particular direction. So, if you speed up, slow down, or turn, you have accelerated. Now, mathematically, acceleration can be defined as being acceleration is equal to the change in velocity over the change in time. And remember, delta always means final minus initial. So, to calculate the acceleration, we take the final velocity of an object minus the initial velocity of an object divided by the time needed to implement that change. And when we do that, we end up dividing meters per second by seconds. And so we can either call it meters per second, which makes sense but sounds weird. Usually, what we'll do is we'll just condense it into meters per second square, however. All right, let's look at a couple examples. So here I have a car. By the way, this is how I draw cars. Get used to it. You're going to see a lot of these is here. Okay, so and I draw these little lines to show like the relative speed. Okay, so I see this car speeding up because those lines got long. All right, so this car was originally going to the right, the positive direction at 10 meters per second, and then 4 seconds later, it's going 30 meters per second again in the positive direction. So if I want to calculate what the acceleration is, I would say, well, final velocity 30 minus initial, which is 10, divided by the time taken needed to make the change, which is 4. My phone is ringing. Hang on a second. That's okay. I get 5 meters per second squared in the positive direction. So basically, if the object is speeding up in the positive direction, that's a positive acceleration. Similarly, if an object speeds up in the negative direction, then that's a negative acceleration. So here the car is initially going 20 meters per second in the negative direction to the left, and 3 seconds later it's going 50 meters per second in the negative direction. So I know that it's got a negative acceleration. So let's just go ahead and calculate that using the equation acceleration equals Vf minus Vi over delta t. So when I do that, I'm going to say the final was negative 50 minus the initial was negative 20. So negative 50 minus negative 20 is, wait a second, is 30 divided by 3 gives me negative 10. Okay. This negative then means its acceleration is in the negative direction. And since it was moving in the negative direction, it ended up going faster. But what if it was the other way around? Okay, here in both cases, my car is traveling in the positive direction. But notice it was initially traveling 30 and it ended up traveling 10. So it's slowing down in the positive direction. Well, that tells me it's got a negative acceleration. Let's just see why. Again, I'm just going to use this equation here. When I do, I say the final 10 minus the initial 30 divided by the time needed to make the change 5 gives me negative 4. So I'm accelerating in the negative direction while moving in the positive direction. And when that happens, the object slows down in the positive direction. Same thing is true in the negative direction. Okay, so here I'm starting out going 50 in the negative direction, but I end up going only 20 in that direction over the course of 10 seconds. So if I calculate this out, what I'm going to get is negative 20 minus negative 50 over 10 gives me positive 3. So even though the object is moving and has a velocity that's in the negative direction, the acceleration is in the positive direction. And so what that ends up doing is it ends up slowing the object down as it moves in the negative direction. Now, what if I have a situation like this? The car was going, say, 30, and 5 seconds later, it's still going 30. And we'll assume there wasn't any variation inside here. That means I have an acceleration of 0. So although the car is moving, albeit fairly quickly, it still has an acceleration of 0. There's been no change in its velocity. What about a situation like this? In this case, the car was going 20, and then a few seconds later, it's still going 20. And again, it never changed speed. The spell number said 20 the whole time, but it did change direction. Well, if you keep in mind that velocity is a vector. So here I had 20 meters per second, let's say north, and then a few seconds later, I was 20 meters per second west. Well, if I change direction, I have accelerated. Now, we're going to call this a centripetal acceleration. It's a topic we'll study all on its own later in the year. But do know that if I change the magnitude or the direction of velocity, that implies acceleration. Now, let's just look at this. So since acceleration has a direction associated with it, that makes it a vector quantity. And so when we're looking at motion problems, we need to consider both the direction of the velocity vector and the acceleration vector. So look here. If the acceleration vector is in the same direction as the velocity vector, then the velocity's magnitude will get larger. It will speed up in whatever direction it's going. So in this case, it's moving in the positive direction. the acceleration is in the positive direction. Since the acceleration is pointed in the same direction as the velocity, its velocity will increase in magnitude. On the other hand, if its velocity was in the positive direction, but the acceleration was in the negative direction, then what would happen is over time it would end up going slower. So the magnitude was fairly large, and the magnitude got smaller because the acceleration is pointing the opposite direction from the velocity vector. And now it helps to sort of think this through. Okay, 'cause I know that last one sometimes throw kids for a loop, but think about this. Okay, so I initially have this object traveling in the positive direction with this velocity vector here, right, denoted by the longer arrow, and the acceleration vector is pointing the opposite direction. So it's got a positive velocity and a negative acceleration. Now, what would happen is as time goes by, this negative acceleration is going to decrease the magnitude of this velocity. Check in a moment later, and now we see the velocity has gotten smaller. It's slowing down in the positive direction because there's a negative acceleration. Well, if this process continues, eventually what will happen is uh, that I will reach a velocity of zero. It will stop moving in the positive direction. And then what's going to happen? Now the acceleration is in the negative direction, so it's going to start picking up velocity and getting faster in the negative direction. So you can see that acceleration, it's if it points the negative direction, eventually this object will end up moving in the negative direction. But it may not do that initially, not until its positive velocity reaches a value of zero, and then it will begin moving in the negative direction. All right, let's switch gears here a little bit and look at some nuts and bolts of how to solve some acceleration problems that we might encounter in this class. Okay, so a classic one is I just take an object and roll it down a ramp. All right, so let's just say I have a ramp that's 6 meters long. The object starts from rest, has a velocity of zero. I don't have a way of knowing what the final velocity of it is, but I did time it. I just timed it. I let it go. It rose 6 meters, and at the end of it, it took 3 seconds to get there. And I want to know what is its acceleration. Now, there's a little bit of a tricky problem here, so let's just work our way through it because I can't just say change in velocity over time because I don't have a way at this point of knowing exactly what that final velocity was. But there is a little trick we can use, and that is there was an average velocity here. It started off at zero. It ended up with some unknown, final value. But I do know that the average velocity means the total distance you traveled divided by the time it took to travel. So I can say, well, your average velocity is going to be your delta v, your delta x over time. So 6 meters divided by 3 seconds, the average velocity was 2 meters per second. Now it started off at zero. It ended up in something faster, but the average was 2. Now that I know what the average is, I can do this. I can say, well, an average of 2 data points would be first data point plus second data point divided by 2. Right? That's what an average is, right? So I'm going to substitute this in. I'm going to say, well, since the average velocity was 2 meters per second, the initial velocity was 0. The second data point, I don't know, but I'm going to solve for it because I'm going to divide by 2 because it's an average of 2 data points. And that gives me 4 meters per second, which kind of makes sense, right? If the average was 2 and it was accelerating at constant rate, well, then the final velocity should be double that, okay? So that's a technique. Now we know the final velocity. We still know the acceleration. So now we had to go back to that acceleration equation to solve for that. So then we say, well, the acceleration equation tells me its acceleration is final velocity minus initial velocity over the time taken to make the transition occur. So my final one we just solved for was 4. We used the average velocity equation to do that. The initial velocity was 0, and we know from before that the time needed to do it was 3 seconds. So I get 1.33333 meters per second square. Now, one thing we'll often do in this class in labs, and they often have questions of this category on the AP test, is using a thing called a photo gate. So a photo gate basically will tell you what the time is that an object passed a given point. All right, so usually it's like a laser beam. When you break the laser beam, it causes the clock to start, and when you stop breaking the clock, basically it is a timer that will be toggled by when the beam is broken and unbroken. Okay, so here I have this object. The length of this cart is 22 centimeters, 0.22 meters, and I release it, and as it passes by this first photo gate, it starts the timer when it reaches it, and when it passes it, the timer stops. So when it blocks the first photo gate, the timer starts. As this rolls past, and now the light is unblocked, it records how much time that was. And the time was 0.1 seconds. It took this one 0.1 seconds to pass the first photo gate, but it's on a slant, so it's accelerating. So you know what? If it took 0.1 seconds to pass this one, and now it's speeding up because it's rolling down a ramp and accelerating, it better take it less time to pass the second photo gate, and it does. In this case, It reached this photo gate at time t equals 1 second, but it moved beyond that photo gate at t equals 0.04 seconds. So here it took 0.1 seconds to pass. Here it took 0.04 seconds to pass. It was accelerated. I should, with this data, be able to figure out the acceleration of this object. And the way I'm going to do this, I'm going to use this information here and this information here to solve for the average velocity here and the average velocity here, and then divide by the time it took to change between those two average velocities. All right, so work with me here. Okay, I'm going to move myself out of the way. Can I move myself? Good, there you go. Okay. So at photo gate 1, the distance traveled was the length of the cart, which is 0.22 meters. So 0.22 meters divided by the amount of time it took to pass here. So it's the difference between these two, which is 0.1 seconds. So that gives me 2.2 meters per second is how fast it was traveling through here. Now remember, I said it should be faster when it goes through here, and it is, because in this case, I'm going to say 0.22 divided by 1.04 minus 1, which is 0.04 seconds. And when I calculate that, I get 5.5 seconds. So it went from 2.2 meters per second to 5.5 meters per second. It's speeding up. Its magnitude of velocity has increased. But what's the rate of acceleration? In order to know that, I need to know how much time it took to do that. And that's kind of a little bit like, do I use the time when I reached the photo gate? Do I use the time when I left the photo gate? And what you do, you use the median time. So I'm just going to take the median time here and the median time here to calculate the delta t for the purposes of solving for the acceleration. So I know now what the final velocity was. It was 5.5. I know what the initial velocity was. It was 2.2. So that's my delta v. To find the time, what I'm going to do is I'm going to say, well, what was the median time here? Well, the median time here would basically be 0.05 seconds. And the median time here would be 1.02 seconds. That's halfway between here and here. So my final velocity, instead of calling it this one or this one, I'm going to use the median of these two. 0.02 is my final time. My initial time is the median of these. So not this one, but halfway between 0.5. And when I do that, I get 3.4 meters per second squared. Now, this is a positive value. So when we're dealing with things on a slope, that's one of those cases where, you know what, it's up to us to decide what to call positive. And one of the tricks we often use is to say, you know what, in a situation like this, I'm just going to set the motion of initial, the direction of initial motion as positive. I'm going to say this direction is positive, so that direction is negative. Remember, there's nothing inherently positive or negative about right, left, up, and down. It's just what we tend to choose for consistency's sake. But in a situation like this, it makes more sense to just choose the down ramp direction as being the positive direction. Now, gravitational acceleration is something we need to pay attention to, because it's one of those things that you just assume to know. All right. So if I take an object and I drop it, like Galileo Galilei famously dropped two objects off the Tower of Pisa, in order to illustrate an important point. So I don't know if you remember the story, and there's some debate as to how true it is, but basically, everybody assumed that heavier things fell faster than lighter things because they seemed to hit with more impact, right? But it turns out he did the experiment and said, well, that's not true. You take a heavy object and a heavy object and a light object, you drop them, they reach the ground at the same time. They have the same acceleration. And this has been borne out over time. And so we refer to this as gravitational acceleration. We symbolize it with the little letter g. So the little letter g just refers to, technically what it means is gravitational field strength. But for the purposes of this first unit, we'll just call it the acceleration of gravity. Objects near Earth's surface that are accelerating in a state of what we call free fall, there's nothing working against their motion, they're going to accelerate 9.81 meters per second squared. Now, here's the thing. This comes up all the time because it's such a handy way of having things accelerate. We have things roll downhill and drop, and so it's the force of gravity that's acting on them. But 9.81 is a hard number to work with. So for giving ourselves 2% error, we're going to round this to 10 meters per second squared on all problems that we do in this class. The only time we're going to use anything different from that is if we're doing a lab where we really need to know the difference. Okay, so on labs, I want you to use this, but on practice problems, I want you to use this. So in class examples, I'll use 10 meters per second squared equals g. So gravitational acceleration is always pointed towards the ground. And so in most cases, we're going to use that convention. We're going to say down is the negative direction and up is the positive direction. So most of the times when we use G, we're going to substitute it with negative 10, or if we're on a lab, negative 9.81. You can come in. Hey. So I had some students coming in, but I'm going to keep on putting this together. So let's just look at this. So I have a person dropping a rock off a tall building, okay? And a person looks out the window and sees it go by a window at 34 meters per second. I wonder how long it's been falling. So I can use the equation. I can say, look, the acceleration is negative 10. Okay, that's g. That's the gravitational acceleration. It's falling in the negative direction. So I'm going to call this negative 34 meters per second. It dropped from rest. So the initial velocity was 0. And I just want to solve for delta t. I get 3.4 seconds. Let's try another one. Last one. I've got a cannonball that's moving upwards. Now, as it moves upwards, it's going to slow down, right? So what I want to know is if when I first check in on it, it's traveling 58 meters per second. I want to know how fast and which ways it's going to be traveling 4 seconds later and 8 seconds later. Let's just use this equation and see if we can figure that out. So I'm going to call down the negative direction. I'm going to call up the positive direction. So that means the acceleration is equal to delta v over delta t. Hang on a second. Okay, thanks. All right. So I'm going to substitute for a negative 10. That's g. That's the gravitational acceleration. Uh, and then I'm going to say, all right, well, the final velocity, I don't know what it is. That's what I want to solve for. I know the initial velocity was in the positive direction. So this velocity is positive. All right. Remember, it's always final minus initial. So I'm subtracting a positive value. But the acceleration is negative. And the time was, let's see, how fast? 4 seconds later. So I divide by 4. I find that it's traveling 18 meters per second. And I get a positive value here. And since I get a positive value, that tells me it's still moving in the upward direction, which we've set as the positive direction. But if I check in on it 8 seconds later, it's a different story. All right. So again, A equals delta V over delta T. A in this case is gravitational acceleration G, which we'll use negative 10. We'll use negative as we'll use down as negative direction. So I'm going to say negative 10 is my acceleration. I'm solving for my final velocity. The initial velocity was upwards, so I'm going to subtract. So it's going to be, VF minus VI, and for VI, I'm going to use positive 58, and I'm going to use for delta T 8. But when I do this, what I get now is I get negative 22, okay, because when I multiply this through and then uh, subtract, I get negative 22, which tells me it's now moving in the downward direction. It's already past this apex and it's now coming back down. So this is the power of the directional component of vectors. The positive and negative values are going to let me know which way the object is moving, not just how fast, but which way. So it's really important when I'm working with these acceleration problems to be very particular about paying attention to the directional notation of the vectors, of the acceleration and velocity vectors and displacement vectors. Okay, thanks for watching. Sorry this one took a while.